Hello everybody. In this short video I'm going to be showing you some examples of polynomials and we'll be starting to discuss their various properties. So let's just remind you of what a polynomial is. It's an expression that looks like this one. Each of these units, which is made up of a constant, a number, times x to a power, is called a term. This power is if it's the biggest power of x, it's called the degree of the polynomial. Otherwise, it's just called power of x. This term is the leading term, and so the number we multiply by is called the leading coefficient. We're going to use that term a lot. And another thing that's important is that each of these powers is an integer. So the degree of the polynomial is an integer, a whole number, positive. And then we write it in such a way that they decrease as we go to the right. The last term that has x to the power of 0, which is just 1, is called the constant term because it's only made up of a number. So let's look at some examples. Here's a polynomial. I have 3 times x to the 7 plus 2 times x to the 6th plus 5 times x plus 1. So this is my leading term because it's the highest power of x. The degree is 7. And the leading coefficient is 3. Another way that we keep track of the coefficients is by numbering them. So a sub n refers to the number that we multiply the power the number we're multiplying by when x is raised to the power n. So if x is raised to the power of 7, that coefficient is labeled a sub 7. So a sub 7 is 3. A sub 6 is the number we multiply x to the 6th by, so that's 2. A sub 5 is the number we multiply x to the 5th by, but we don't have any x to the 5th, so this is 0. There's no x to the 4th, so a sub 4 is 0, a sub 3 is 0, a sub 2 is 0, but x to the 1 is multiplied by 5, so a sub 1 is 5, and a sub 0, the constant term, is 1. And let's just take a look at this polynomial so we can start to get a sense of what the graphs of these polynomials look like. So in my calculator, I'll put in 3x to the 7 plus 2x to the 6, and what did we have next? Plus 5x plus 1, plus 5x plus 1, and we'll check out the graph. So it looks kind of like the x cubed graph a little bit. It's got symmetry across the origin in this case. Well, actually, I think if we zoomed in, it wouldn't, but it looks almost as if it had symmetry across the origin. And it's got, as we move to the left, it drops down. As we move to the right, it drops up. We'll formalize those observations in the next video. Okay, so here's another example. One of our happy quadratic polynomials. So this one is degree 2 because the highest power of x is 2. Its leading coefficient is also 2. And you know what this one looks like. It's just going to be some type of wonderful parabola. And if I asked you to graph it, you should know how to do it by now, after all the practice you've had. So here's our parabola. As we go to the left, it goes up. As we go to the right, it also goes up. So it's sort of the opposite of that last one, which had one leg going down and one leg going up. This one has a minimum value. There's no breaks or holes in the graph. It's very smooth. These are all things that are true for all polynomials. 3x minus 1, this is a linear polynomial. We know it looks like a line. All that means is that it has degree 1. And we know what this looks like. It's going to be a line with y-intercept 0, 1, and with slope 3. So again, we know what this graph looks like. It's a nice line. So this one, as you go to the left, it drops down. As you go to the right, it raises up. No breaks or holes in the graph. It's very smooth. It's not jagged like the absolute value function. So the other thing to notice before we move on is that all of these examples, the domain was all real numbers. We never have a square root. We are never dividing by anything with x in the denominator. So there are no problems. We can plug in whatever we want for these values of x, because all we're doing is raising x to a power, and you can raise any number you want to a power. So let's look at some non-examples and see why they're different from polynomials. So this is not an integer. So this is not a polynomial. Oops. Not a polynomial. Polynomial because it has a power which is not an integer. And what does the graph of that one look like? So let's check it out. If we plug in x raised to the 0.5 plus 5x, let's look at a slightly better window, just so that we can see more of the graph. But you'll notice that there are no values for x that get assigned y values. So the domain of this function is not all real numbers. We actually know that because this is the square root of x plus 5x. So we're only allowed to plug in numbers bigger than or equal to 0. And that wasn't true for the polynomials. Polynomials, we could plug in anything we wanted. This second one is also not a polynomial because we have an x in the denominator. And you'll notice that the domain of this function is not all real numbers either, because there's the potential for the denominator to be 0. So let's see what it looks like. 2x squared minus 3 divided by x cubed plus 5. Notice how carefully I used the parentheses here. Oops. Let's go back to a normal window. So this graph, it almost resembles the 1 over x graph. It's got this vertical line called a vertical asymptote that we'll talk about later, and a horizontal line called a horizontal asymptote that we'll talk about later. These are just lines that the graph gets very, very close to but never touches. That's how you should think about it for now. So we see the domain is actually all x not equal to the negative cube root of 5. If you plug that in here, or cube root of negative 5, either way. If you plug that in here, then you would get 0 in the denominator. So this is actually the cube root of negative 5, giving us the vertical asymptote. We'll formalize that in another video. So finally, absolute value of x. This is not a polynomial because it involves operations different than just raising to a power. Just the fact that it involves the absolute value makes it not a polynomial. And if we look at that graph, so I go into the catalog and click absolute value, you know what that looks like. It's that V. So it's got this very jagged corner. So from our non-examples and our examples, we can see some similarities and differences between them. All of the polynomials had nice smooth graphs, no holes. The domain was all real numbers. And that wasn't true for these graphs. So here are some facts about polynomials. The domain will be all real numbers, always, unless we restrict it. Secondly, they have continuous graphs. Continuous just means unbroken, no holes or asymptotes, those lines that we saw in the graph of non-example number 2. So you wouldn't get something like this. This is not a polynomial. They also have smooth rounded turns. So this is possible, this is good, this is no good. That would be jagged. So there are your basic facts about polynomial functions, and we'll be exploring them. Our main goal is going to be how to graph them. And it's going to be really important for us to be able to find the x-intercepts and the zeros. But we'll definitely use these observations and properties that we just came up with and the terminology that we've talked about in this video. All right, so good luck with that first web work, and I'll see you again soon.